Let's analyze the convergence of the following series. Let's find if the sum n equals 2 to infinity of the square root of n divided by natural log of n squared times n squared plus 1 is convergent or divergent. So in this type of problems, the only thing that we need to do is we need to find whether or not this can give me a number or not. In other words, our only two options are either that the expression is convergent or divergent. Those are the only two options. So what we're going to do is we're going to find out if this expression, this series, is going to give me that number. We are not interested in a number. We're just interested in finding if that number exists or not. In the case there is a number, then that number can be found using a computer or a calculator. In the case that the number does not exist, we know that whatever a computer can give me is actually not true. It's actually not useful for me. So what we're going to do is first we're going to analyze the sequence associated with this series. In other words, the sequence we're talking about is the sequence square root of n over natural log of n squared plus 1. Notice that this sequence actually starts from n equals 2. So this is mainly to avoid dividing by 0 or having any weird number over here. So in that sense, what this means is that the very first term of that sequence is going to be the a sub 2, which is square root of 2 over natural log of 2 squared plus 1. Then the next term will be a sub 3, which is the square root of 3 divided by natural log of 3 squared times 3 squared plus 1, and so on. So one thing that we see out of this expression is that the expression is positive, and also we have that is decreasing. So these are the two important requirements that we need to remember in order to use any of the tests that we have for convergence. So in this case, one test that we can use, because I look at this power over here, is that somehow I can relate this with maybe a p-test. I can also think about an integral test, but the corresponding integral would be something like the square root of x divided by the natural log of x squared times x squared plus 1 dx. And this integral may be a little bit tricky. So I don't want to go this route. I think that maybe comparing this with a power series like this would actually make more sense. So what I want to do is I want to compare a sub n with something that is a little bit nicer. So notice that a sub n, which is square root of n natural log squared n squared plus 1, notice that this is going to be smaller than if I just remove the natural log from this. In other words, we have that removing the natural log will make the fraction bigger. And the reason is because natural log of n is actually bigger than 1. So if I remove this factor, if I remove this natural log square factor, the denominator becomes smaller, which will make the fraction to become bigger. So what I'm trying to do is I'm trying to compare the original sequence with a nicer looking sequence, basically just by removing the things that are inconvenient for me. So again, in this case, by removing the natural log, which is bigger than 1, that means that the denominator of the new fraction is actually smaller. We have that the original one is bigger. So if the denominator is smaller, that means that the new fraction is going to become bigger because we're dividing by a smaller number. In other words, we have that this new sequence in here is going to be bigger than the original sequence. And I can repeat this trick again. I know now that I can, if I replace a smaller denominator, that will give me a bigger fraction. So now I can replace the plus 1, and that will give me a even bigger fraction. In other words, if I now take out this plus 1 that I have over here, that will make the denominator smaller, which will make the overall fraction bigger because I'm dividing by a smaller number. Now, this expression that I end up with is actually a nice expression because that turns out to be a p. That's a power. In other words, if I look at that last expression, this becomes n to the 1/2 over n squared, which is nothing else but 1 over n to the 3/2. This is a p-test. So what I know about this new sequence that I just found is that this is going to be convergent. We know that 1 over n cubed, n to the 3/2 is convergent by p-test. Because in this case we have p equals 3/2, which is bigger than 1. That's our p-test. So what I have is that on the right hand side, this part is going to give me a convergent sequence, which means that this sequence is a number, gives me a series that gives me a number. This series that I just write over here gives a number. It is convergent. And now I know if I follow my chain of inequalities that I just wrote in here, I know that the original one that I was looking for has to be smaller than that. In other words, I have that the original one, square root of n divided by the natural log square of n times n squared plus 1. This has to be strictly smaller than this convergent sequence. So since this side is convergent, this side has to be convergent. In other words, I don't know what the number is, but since this is a positive series and it's bounded from the top, that means that this has to be also convergent. I don't know what the number could be, but I know that there is a number. And that is basically the argument that I was looking for. I was trying to look for a logical argument that could tell me whether or not the original expression was an actual number or not. And because it is bounded by something that is convergent, that means that it has to be convergent. The original has to be convergent. So that is basically what we did. We found an argument, a logical argument, by computing these powers, that the original expression is actually convergent.